I want to talk about how you can determine the average whereabouts of a quantum particle. So in this example, I'm going to take a look at an electron in an infinite square well, and asking sort of where something is really better phrased as what is the relative frequency of occurrence of observing an interaction of that electron to take place within a certain location. And interpreted from the lens of the probability wave function psi, the relative frequency of occurrence is based off summing up the magnitude of our wave function squared. So what we would do would integrate the complex conjugate of our wave function multiplied by our wave function with respect to x over the region wherein we want to figure out how likely is an event, an interaction going to be happening there. Or rather, if I were to do n billion experiments, what fraction of those experiments would have the electron interacting in that region? Now, from a classical picture, if we were to think of an electron as being a particle bouncing back and forth between the walls of the box, then we would pretty much expect it to take about sort of equal amounts of time to be in all places. So we'd expect in any given segment an equal amount of time, about a quarter. So if we're looking at a quarter of the size of the box. Now, for a particle in a box, our probability wave function is equal to a constant a times the sine of n pi x over L. Now, this is a real function. There's no complex dependence, so the complex conjugate should just be the sine. But some folks might say, well, you talked about Eulers identity. Euler's identity can be used to express sine in terms of the square root of -1. So if I write out the sine in terms of Euler's number, the sine of an angle is e to the I theta minus e to the minus I theta divided by 2i, square root of -1 for all of those i's. So to make the complex conjugate, I would have e to the minus I theta minus e to the plus I theta divided by minus 2i. So all of the negative signs end up balancing out the fact that they flip, and we're left with a complex conjugate of sine being equal to the sine itself. And with the cosine, the same thing happens. It's just e to the I theta plus e to the minus I theta is clearly the same as e to the minus I theta plus e to the plus I theta. Easy go of it. Any real function, the complex conjugate is the function itself. So we need to normalize our wave function. So to do that, we would write out our wave function times its complex conjugate, so that gives us a squared sine squared of n pi x over L. And we would need to integrate over all of space. So for an infinite square well, we're starting at x equals 0, we're ending at x equals L. And we set that equal to 1. Now to integrate sine squared, the easiest thing to do is to make use of the trig identity for sine squared. Sine squared can be written as 1/2 minus the cosine of 2 times the angle that we have. So if I look at integrating this, well, the integral of 1/2 with respect to x gives me x over 2. So evaluated between x equals L and x equals 0, I just get L over 2. Now, the integral of the cosine of 2 pi times n times x over L is going to give me a factor of L over 2n pi times the minus cosine of what's inside, not the minus cosine, the minus sine of what's inside. The integral of the cosine is the sine, the integral of minus cosine is the minus sine. Well, the sine of x equals 0 is 0. That term drops out. The sine of x equals L would be 2n pi times L over L. Well, n is going to be an integer that isn't equal to 0. So that means any integer times 2 pi is going to be a multiple of 2 pi, which means the sine's going to be 0. So that dependence cancels itself out. And all we're left with is a squared times L over 2 equals 1. So the amplitude A would have to be the square root of 2 over L. Now if I were to plug that in to figure out the probability of something being within a region, I could write out this integral, and instead of being over all of space, I'm going to integrate through the first quarter of the infinite square well, from x equals 0 to x equals L over 4. So now, instead of a squared, I can just write 2 over L. And my integral is still going to be the integral of 1/2 minus the cosine of 2n pi x over L. That integral is still going to give me x over 2 minus L over 2n pi times the sine of 2n pi x over L. But now I have different limits. Now, at x equals 0, those terms are still both 0. But at x equals L, I have L over 4 times 2 over 2 divided by L. That gives me a factor of 1/4. And then I have minus L over 4. I don't have a factor of 2 in the denominator. I would have 2n pi from my integral, but from plugging in L over 4, I end up getting... I end up getting a factor of 2n pi, yeah. Wow, it's been a long quarantine so far. So, I have minus 2n pi, and here is where I plug in L over 4, so the L over L cancels, and I get 2n pi over 4. So my final result then for the probability as a function of n would be 1/4, which would be the classical probability, times the sine of n pi over 2 divided by 2n pi. So, the lowest case we could get would be for n equals 1. For n equals 1, we would have 1/4 minus the sine of pi over 2. The sine of pi over 2 is 1 over 2 pi. 1/4 minus 1 over 2 pi gives me 0.091, 9.1%. Now, this function is going to be symmetric about the middle of this space. So if I were to look in the last quarter, I would get the exact same probability. So if I were to look in the middle, I'd end up getting a probability of just under 0.82, or just under 82% of the time, interactions would be happening in the middle half. But if I go to n equals 2, the sine of pi is 0. So 25% of my interactions happen in the first quarter, 25% happen in the second quarter, half happen in the middle half. If I go to n equals 3, well, instead of getting 1, I get minus 1. So my probability is going to be a little over 25%. And what we would see would be fluctuations slightly above, slightly below, or equal to 25%, with the size of those fluctuations going to 0 as we get to higher and higher energy levels. And the classical world is just the limit of taking n goes to infinity of this system, which means we end up with a probability for each quarter of 1/4. Thanks for watching.